recording. Okay, so today we're gonna talk about two things, and more importantly, we're gonna talk about something called laziness.
I bet you were looking forward to this one.
Well, to be completely honest, I wasn't. Like, I'm not well versed. Like, I confess, I'm not well versed into laziness, even though I like Haskell. I understand some implications of it, of course, but I'm not. I wouldn't say I'm an enthusiast about it. But I
I
was more
see.
like, as I was reading this, my immediate reaction was like, this is gonna be confusing because I will be I will be confused about whether something is blocked because it's not bound or because it's not yet computed because we didn't demand it yet or something like that. And I was right. When we're gonna get there, I was confused and I will ask questions because I feel
Okay.
that these two concepts, although the book tries very hard to make a distinction about them, it doesn't answer obvious questions from some of the examples, in my opinion. Um,
Okay.
okay, okay. Anyway, so we're gonna make lazy declarative programs, which is very impressive. At some portion here, it will say that it's amazing that they are declarative, which is true. It is very amazing. Uh, Are there any other execution strategies for declarative programs? Turns out that there's a second execution strategy fundamentally different than the usual left to right execution. Well, left to right, top to bottom. We call this strategy lazy evaluation or domain-driven evaluation. This is in contrast to the user strategy, which is called eager evaluation or data-driven evaluation. In lazy evaluation, a statement is only executed when it's needed, and we're gonna have to define what the fuck that means. And I also think the book could be better on that part. So for example, we have these three lazy functions, and we have this D here. Um, and TLDR, we're not going to compute whatever C is, but we will compute what A and B are because we are using them to do this addition here. But this puts us to my first question.
Okay.
Uh, we don't do this through the runtime example. I think the runtime example doesn't go to this level of detail. But at least in intuition terms, I think that when you see this type of expression, I think there are um, there are two verifications that we're gonna be doing now. First, if it's the variable is bound, and second, if it's we can generate its value in a way.
Hmm.
Because let's say that these two lines didn't exist. These will hold, but not because we have to compute A and B, but because they are not bound yet.
That is correct.
But then after they are bound, you can ask a second question now, which is, are they, um, are they, can I generate their values or not?
That's not really a separate question actually. If you go look um at the actual semantics, there's actually an appendix for this, like way there in the book. But if you look at the by need instruction, and we'll get to that in a bit. I think it's a few pages down. It doesn't actually bind the variable.
What do you mean it doesn't bind the variable? The variable is being bound here.
Not really.
Hey, really, it even says down there in the by need definition that binding is a need, the semantics. There are two
Binding.
definitions for by need, right? That's what the book explains. The first one is if we need to do something else, which is this case. And there is the second case, which is the bind. And the reason it does
Mm,
that is because if bind is not in by need, we're going to lose declarativeness. And there is even an example about x equal 3 and x equal 2 that if bind doesn't trigger the activation of the laziness, the two programs will result differently depending on the order of the threads.
Okay. I see. I think I see. Um, okay, this A equals F1 then is not actually binding A. It's just setting up a bind needs trigger on it.
I don't follow. This to me is definitely a bind, but it's not doing the evaluation.
No, it's not a bind. You have to remember, Lemos, that this syntax actually desugars to a procedure call with A as the final argument.
Oh, okay. You mean that because this is a function call, in the desugaring process, this equal is misleading. This is not a bind because this will desugar to a procedure with an output being the variable.
Yeah,
But that's still a bind, right? We're gonna bind the output of the procedure to that.
no, the procedure actually is going to set up a bind needs trigger bound to A.
So it is bind. You just said it's bound to A.
It's going to attach a trigger to A, which is going to run when you try to wait for A's value, or when you try to bind A to something else.
I don't follow. Yeah, I'm very confused about what you said. To me, this is bind because we are
It is,
saying that this is, the result of this is gonna be bound to this in the assignment store.
it isn't quite, because there's a difference between saying, okay, when I need this variable, I want to run this code that will bind it, versus actually binding it to a concrete value. Those are two different things. One leads to the other, but you can actually skip the bind needs trigger, which we have been doing so far, because it didn't exist in our model yet.
Yeah, I'm still confused. I'm sorry. Maybe I'm misunderstanding something, but I think even in the examples it demonstrates that this is a bind. Maybe I'm just getting confused because of the syntax sugar of the function. But well, we're gonna see more examples down there. The thing of the matter, well, let's close this tangent. The thing that matters to me is now we have two questions to ask ourselves when doing this operation, right?
Right.
Which is this bound? Because if it's not bound, I'm just gonna hold forever, given
It
the
actually,
synchronization mechanism.
well, yes, but actually that's the second question first, which is there any lazy trigger attached to this variable? Because if there is, it will run it.
It doesn't, but that's the thing. It doesn't make sense to ask the question first, because if this is not bound at all, not even to a lazy thing, why am I gonna do like I'm just gonna waste time asking this question if it's not even bound.
Okay, let's try
Maybe it's
to.
easier if I show the table that separates the three things because my mind is completely locked on that. So let's just skip a couple of pages. Yeah, I'm talking about this thing. So when you do the like local a in, the a by itself is just declaration. When you do the equals, so when you're making it not unbound, you do the true, specify the function to calculate the variable's value. And when you evaluate what is on the right hand side of the equals, that's
No, no,
evaluation.
no, 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 no. See, Lemus, if you look at the nomenclature here very carefully, you see that bind is only used on 3, not 2. 2 is not binding.
Ah, I see. Yeah, but then this, what does this even mean? You know?
Well, you are. If you want to get down to the nitty gritty semantics,
Ah, okay. So okay, sorry to interrupt you, but this is doing a bind to the trigger section of the store.
yeah, it's not binding the variable, it's creating a trigger and specifying that it runs for this variable.
Yeah, but it's making a connection between the label and something else. That's why I'm using the same verb bind. But now I understand what you meant. The bind
Yeah,
is to a concrete value.
yeah, you shouldn't use bind for both things because that's confusing. The
But that
book doesn't do that.
Yeah, but the book is wrong on this. We were calling bind when you have an unbound a variable bound to a bind and doing a bound to another unbound variable, and it was calling these partial values, and there was still a bind. So
Well, there's a difference between binding two variables together. which constrains their value to be the same thing, and when one of them is bound to a concrete to an actual value, both of them will be, versus creating a trigger that's not going to bind the variable immediately, but can bind it later when you try
But it
to
was
check if
also
the
doing binds with partial values. That's my problem. It was also used this verb to partial values in the store. You were talking only about complete values. And I'm talking that we were doing binds
no no
until
no
now that were partial.
not complete, concrete.
Yeah, okay, so even I agree that concrete and complete are different. We were doing binds to partial values. So what the fuck happened here?
You're not actually binding the variable to a value though.
Here you mean?
On step two on
So
this.
yes, I agree. You are doing an assignment between a name and something in the trigger section of the store, which you're gonna which I jumped, right? I don't remember if it comes before this or after. I think it comes before. We're gonna see that the store will receive and it will be augmented with triggers, and we
Yeah.
are doing a relationship between a label and that. But for some reason, it's using a different verb for that. It's using all of these sentences, specify the function to calculate the variable's value. So that was my mistake. It's not calling this particular relationship a bind, even though to me it makes all the sense to call it a bind, but you were right. Now I understand my confusion. The bind is only after we are done doing the calculation that is stored in the trigger section of the store.
Yeah.
I dislike this change. To me, all of them should be called binds, but that's fine. Now at least I understand why I was getting confused. Uh,
Nomenclature. It's hard.
I would say this is inconsistent. If we have binds with partial values, why the fuck we are differentiating binds to lazy functions?
Well, if you bind a variable to a partial value, you are still binding the variable to a value. It's just not complete.
Yeah, but there is some sort of thing hanging in the partial value. Although it's not hanging because of demand, it's hanging because of boundness. Those are two
Uh,
different sorts of
let me try to put it this way. A partial value is basically a shell with potentially holes inside of it that you can fill in later, right? But it's still a thing.
but there's holes. There's absence of things. That's where holes are.
But it's still a thing in itself. Like you can try to check its top level properties, which is a terrible name, but I just literally came up with it. Like, say for instance that you're trying to bind a partial list in a variable, right?
Sure,
And let's assume that you have the first cell already because it's a partial value, right? You don't have the tail and you don't have the first value, but you have the first cell. You can
sure.
do things with it. You can like
You
check if
could,
its tag is the pipe to see if it's actually a list cell, right? And things like that.
sure, sure. Well, but
Which
with a lazy function, you can still do things with it. You can still put in definitions of things. Like you can still do stuff with it. Like it's the same logic as you
mm,
just said.
not really, because if a lazy function, the value has not been materialized yet. It will only be materialized later.
But that doesn't matter to your example. Your example was it has holes, it's partial, but you can still do useful
No, no,
stuff
no,
with
no,
it.
no,
That's
no,
the
no, no.
same
It's
here.
not. No, 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 it's not, because in the first example, you had a shell. There were holes inside of it, but you had the outer shell. Here, you don't even have the outer shell yet. That's going to wait until later.
No, yeah, I agree that there's no outer shell, but you can still do things with it.
Not really. You can only force it.
No, that's wrong. You can do also this, and this is not forcing it.
Here's actually creating the trigger to begin with, right?
Exactly. You have to first create it, and that's what I mean with that you can use it. You can pass this F1 to whatever, doesn't matter. And then later they will be materialized anyway. But you can still put this in a higher order function, for example. You can do a lot of things with it. So why are we doing this differentiation? Again, I don't like it. To me, just confuse me. That's exactly what happened. Um, well, anyway, but this I don't want to waste too much time on this. I already got one of my answers fulfilled, which is that now we need to ask ourselves about the thing being bound and if the thing has a trigger or not, so we can generate the value by need. And we're gonna have to go through whatever by need means, and we're gonna talk about that. Uh, so yeah, so then there's the importance of lazy evaluation. It doesn't talk about this in here explicitly, but there are programs that they can only halt because they are lazy. I think that could be also explored in here. But it talks about other
Ah,
things, for example, right? So it talks for in programming the small, it can help in the design of declarative algorithms that can be good amortized or worst case time bound. So you're going to see this.
it actually, yeah, it actually mentions this later when it talks about evaluation orders.
Okay, but this is not this chapter, right? This is in the future.
Yeah, it's in the future.
Okay. For programming the large, you can help modularize programs. This is explained in detail by this article. An application where a producer sends a stream of data to a consumer. In an eager model, the producer decides when data has been sent. This is not really true because we've seen last time that we can do the opposite without having implicit laziness. But if you do the opposite and you don't want to use implicit laziness, you're going to have to do explicit laziness where the synchronization mechanism is done by the programmer. And that sucks, as we've seen, but you
Yeah, it's
can
kind
do
of a
it.
pain. Yeah, it's kind of a pain.
With laziness, the consumer decides. The lazy computation model of this book is slightly different from lazy evaluation and is using functional languages. I didn't know that. So apparently, since these languages are sequential, lazy evaluation does coroutining between the lazy function. And this explains why he explained coroutines before, which is essentially the idea that you can interleave computations non-preemptively.
Yeah.
We've seen this before. We study laziness in a more general context of concurrent models. So we're gonna actually make concurrent lazy declarative programs, which
Yeah.
is very cool and very powerful. Then it has a summary here that doesn't matter. And then we're gonna define what the fuck we mean by the by need. And we're also gonna have to add a new thing to our VM, which is called the by need trigger.
Yep.
Uh, so how can both data-driven and demand-driven concurrency coexist in the same computation model? The way we have chosen is to make data-driven concurrency the default and to add an extra operation to introduce a demand-driven part. So essentially like normal languages, Clojure, OCaml, they all do this.
Yep.
It is reasonable to make data-driven concurrency the default because it's much easier to reason about the time and space complexity to implement efficiently. We find that often the best way to structure an application is to build a data-driven fashion around a data-driven core. I didn't understand what this means. Are they talking about that the built-in compiler exclusive things will be demand-driven, but the compiler developer will be using data-driven
No, no,
things that are
no,
using
no. This is
demand-driven things under there?
no. This is talking about structuring an application. Like for instance, suppose you want to print. I don't know. Suppose you want to print prime numbers or something, right?
The Hamming problem, right?
Yeah, I have that in my head because I just recently read this, right? But basically, um, the natural way to do that, if you will, you make a is probably to make a lazy list with all of the primes and then just print as many as you want, right? You have you're doing data-driven stuff around an infinite list, which is demand-driven.
Oh,
That's
okay, so
kind of the
what's what they
point.
mean? Okay, so we're gonna add a new instruction called by need to the kernel language. The by need has the same effect as the statement of the thread. Both statements can produce p in its own thread with argument y. The difference between the statements is when the procedural call is executed. For thread, we know that py will always be executed eventually. For by need py, only if it's demanded. And then we go to my next question, which is this program, which is essentially like a thread. So this is a procedure that is receiving an A. And this is doing like a square of 111, and the argument is going to be the y to this procedure. And then we do browse y, and then it says this displays nothing without that displays y without calculating its value. What? What do you need? I'm literally asking to print its value.
No. You're browsing the variable y, which currently doesn't have a value but has a trigger attached to it.
But I want to see its value, right?
Not necessarily. You may just want to see the variable for now.
Wait, so in this language, printing the value of a variable doesn't trigger the trigger?
No. Browsing a variable doesn't trigger the trigger.
But what would be the reason that I want to see well, I would want to browse a variable?
Maybe you're setting up a visualization that you want to accompany when the variable actually becomes bound.
No, yes. In the case of data flow variables, I can understand, but this is not what we are talking about. We are talking about the activation mechanism to trigger the trigger. And as far as you said, and as far as it's written, asking to display it is not a valid trigger for it.
No. Browsing it, specifically using the browser, doesn't
No,
trigger
no.
it.
Display it. This is the verb being used here. We are using the browse function to try to display it, but we are trying to display it.
But if you try to display it using something else, that may trigger it.
Yeah, but that's so
That's kind
weird. Like, to me, that's
that's
exactly one of the easiest triggers ever in a lazy
that's
language.
because browse is not actually, well, the implementation of browse is not actually declarative.
That's fine, but uh, like we're gonna go through, yeah, the semantics of what it needs to be needing something, right? We're gonna talk about that. And I was very surprised and confused why this particular side effect is not listed in there. To me, that's one of the most fundamental cases where you should ask the lazy to kick off. Okay,
Why?
because this is the first thing you would do debugging a program. This is
Like if you
making,
if
like, let's say for a moment that there is another display function which is called browse lazy that triggers the laziness. If that's the case, that's fine. But if I have a lazy thing in my program anywhere, I will use browse lazy instead of normal browse. So what are we losing by not making browse a trigger?
what well, you're not actually losing anything because you can always just trigger it manually afterwards or beforehand.
No, I'm gonna have to do something extra just because browse doesn't, like, crazy.
The point
But
the
okay,
point, Lemos, is that browse doesn't actually disturb the things it's trying to show you.
it doesn't disturb.
Yeah, remember when we were having trouble debugging the compiler in Karuta where we added a debug and that changed the program that we were emitting, which changed the behavior that we were trying to observe. Remember that?
That was on in Karuto. That was in Chime,
No, it happened in Karuta as well.
where the act of printing changed the output.
No, not the act of printing. We were adding a debug instruction, but we were actually trying to observe the behavior of a particular code
Ah,
structure that
okay, no.
disappeared.
Yeah, it was because when we inserted the debug, an instruction that was participating glued to the head, which has a different code generation than if you have a head and the first and then second, third, and so on, that changed the code generation. That's true, that happened.
Yeah, that's the point. If browse doesn't actually trigger the thing, that means it's not going to disturb the thing that you're trying to observe, you see?
I understand that point of view. I find it less useful than what I said. If I want to browse it, particularly for debugging purposes, I want to disturb it if this is lazy.
What if it's infinite?
Then it does what it already does, which is future,
But how
future something or whatever.
but how can it tell if it's infinite or not?
Well, it already does that.
It doesn't.
It does. We can go to the example of the Hemming problem, right?
It
Where
doesn't. The reason it doesn't force the infinite list is because it's lazy and it doesn't force lazy things, you see?
no, wait, am I getting yeah, it already does it, right? It already can identify that something has a future on it, so that's fine. It already does it.
Yeah,
So yeah. So
and
what's the problem?
the problem is that if you say, okay, browse should force lazy triggers, then if you have a lazy list which is infinite, by your logic, you should force the list entirely,
Sure. I rather have
which
that than
means
I have nothing.
which means you're going to be stuck forever because the list is infinite.
That's not how that works. Well, at least in Haskell. If you make a an infinite lazy list in Haskell, it will just be printing all day. It's not gonna be stuck there, like with the cursor blinking. That's not how that works.
Okay, fine, it's going to print forever, but the point is, it's going to force the entire list, right? Which means eventually you're going to run out of memory.
No, yeah, I agree with you that that's not the best behavior. But that's best than nothing.
But
If
it's
I
not
do
going to show
browse
no,
y and prints nothing, is that a
it's not going
boundness
to
problem or is that a
it's not going to
laziness problem?
it's not going to show nothing lemon. It's going to show a future because that's what y is at the moment.
Oh, so at least it will display miss something in here. It doesn't say that, but you tested this.
No, it says that it displays y without calculating its value. The only way to do that is to print something like underscore future, like it's shown below, right?
Well, there's no well only down there. But what you're saying is that if I try to print the y here, well, first of all, as you said, displaying it doesn't trigger it, and it will display a future in surrounded by brackets.
Yeah.
Okay, that's at least something. I thought it would display nothing. Um, I keep my comment that it's more useful with this triggered laziness, as it does in Haskell. But okay, at least this is something.
If you try to print it to the console, then it would trigger it because you have to know the value in order to turn it into a string. But the browser
But this
doesn't
will
do
open
that.
a window. This will open a window with doing display on it. It's worse than printing to the console. It will open a dedicated window for it.
No. And the reason for that is because the window is, well, it exists over time, right? It's not like the console where you just print to it and then you're done. In the window, you keep re-rendering the window every frame, which means if the lazy value is forced later, you actually have a chance to re-render it with the updated value after it's bound to
Yeah,
something.
no, I agree. This is better because it's interactive, right? The window it keeps the window open, and then you can update over time the value if it just got bound, for example. I understand the rationale behind the decision. I'm just saying that for me, I would rather make this trigger the laziness because that to me it's more useful as I'm debugging a lazy program. But I'm gonna have to do something artificially just to trigger that because in here the display doesn't. So I can do I can do an operation with it, or I can do a bind. Those two things will trigger the laziness, but the display by itself it won't. Because to me this would be a perfect example that I would want to see the value of y. Invoking an operation that needs the value of y, for example this, or wait, will trigger the calculation of y. This causes this to be displayed. We implement by need in the computation model by adding just one concept, the by need trigger. In general, a trigger is a pair consisting of an activation condition, which is a predicate, and an action, which is a procedure. When the activation condition becomes true, then the action is executed once. Yeah, this is also a hint on an optimization we're going to be able to do now. When this happens, we say that the trigger is activated. We distinguish between programmed triggers, which are written explicitly by the programmer, which we've seen before, and internal triggers, which are part of the computation model. And then we we introduce an extension to the execution state, which is these are the changes to our VM,
Yep.
and we're gonna add a new section to the store called the trigger store. The trigger store contains all the binary triggers and it's initially empty. I don't remember what the E is, but if it's undetermined, then add this trigger to the trigger store. Otherwise, if EY is determined, then create a new thread with initial semantic statement.
Use the environment which has all the stores.
Makes sense. And then we have some algorithms to trigger for the trigger activation. And then, yeah, this is what I want to talk about. So the needing a variable. Needing a variable. What does it mean for a variable to be needed? The definition of need is carefully designed so that the lazy execution is declarative. A variable is needed by a suspended operation if the variable must be determined for the operation to continue. And I find this definition very weird because this is also what we've been doing for the data flow variables. So for example, in this Z here, let's say that this thread doesn't exist. This Z would suspend because he needs a variable in order to the operation to continue, but not because of the laziness. So I found that's where it started to get gray for me, these two things.
No. That's kind of the point. It's basically saying, okay, um, we're going to very carefully define the semantics of needed so that it kind of overlaps with um, the situations where you would suspend. So that okay, instead of suspending, we're going to run the trigger, and and then instead of just suspending, we're going to run the trigger, which is going to unblock us eventually.
Yeah, so you suspend and then you ask yourself, do I have a trigger for it? If I don't, I keep myself suspended, right?
Yeah.
Yeah, so that's
Well,
what I said.
technically, it still stays suspended even if you run the trigger because the trigger runs in a separate thread. But
Yeah,
yeah,
we have to wait until it gets done. I agree, but that's where I said I started to get confused because this is getting very very similar to the data flow behavior of like I'm
that's
suspended
the
and I have to wait until something is bound.
that's deliberate so that okay, I need the value, which means I'm suspended because the variable is not bound. Which means actually because the definitions overlap, that means we can check. Okay, do we have a trigger? If we do, we run it. You see?
Yeah, but until this point, when I read this, I was very confused about. Wait, aren't those things the same thing then? But then when we go to the table. This table helped me separate them again, back again, because I got completely confused when I saw this. I was like, okay, I'm starting to think that they are the same shit, but they are not because of the table down there.
Yeah, they're not quite the same. Especially because this notion of needed, if you pay attention later, once you need a value for the first time, or the value of a variable for the first time, you always need it.
Yeah, yeah, this is also written in the book.
Yeah.
There's a second definition of needing it, which is a variable is needed if it is determined. If this were not true, then the demand-driven query model would not be declarative. And then we have this example in which we're trying to bind x to 3 and 2 in two separate threads. And if this doesn't, let's say that this runs first. If this doesn't activate, we wouldn't get the fail that we would otherwise. If the order was changed, the order of execution was different. Because again, in order to keep the declarativeness, we need all the orders to have the same outcome.
Yeah.
So they all should fail. Um, Let us conclude by giving a more subtle example. This is weird to me. This is another question. Should the comparison x equals y activate the trigger of x? Yes, of course. But the immediate answer is no. And I was like, what the fuck are these guys talking about? If I don't have these to compare, like I
But you
need to
don't need
suspend.
to because but you don't need to compare them because the variables are bound to each other. You already know they must be equal.
Oh, you mean if you run these first?
Yeah.
That's not written here.
Well, actually, because this is all inside of threads, right? What's going to happen is the equal comparison is going to block, but then when you get to the x equal y on the other thread, it's going to unblock because the two variables are in the same equivalence set.
Yeah, but if you run these first, how in the fuck this should not try to activate the trigger? If you let's say that you run 3, 1, and 2, okay?
Okay.
On this will definitely block, right?
Yeah, if this runs first, this will definitely block.
Okay, and then we run this. But X is being used in this comparison. How this is not going to activate the trigger for X?
Because it doesn't just need X, it needs Y as well.
So it needs both hand sides of the thing?
Yeah.
Wait, you're telling me that if you have um, that will only trigger if you if this is the only piece missing? Is that the semantics?
Actually, it will only trigger if you can trigger all of them, or if this is the only piece the missing.
That is
In the
also
case of
not written here. Okay? Because in my mind, I have two pieces that I need to resolve in order to not be suspended. So this fits with the first definition. A variable is suspended by a suspend operation if the variable must be determined for the operation to continue. So I was kind of thinking like that. But what you said is you only going to be triggered if you're the remaining piece, or
uh,
if I have all everybody else.
yeah, because if you even if you trigger X, you're still blocked on Y, so you shouldn't trigger X yet.
No, you should trigger both. In my mind, you should trigger both.
No, but you can't trigger both because Y doesn't have a trigger.
You don't know that. Maybe there's a fourth thread.
Well, if a fourth thread adds a trigger to Y, then that changes the picture. Then you say, okay, X has a trigger, Y has a trigger. They both have triggers, and I need both of them, so let's run the triggers.
Wait. So the only reason you know that you should not run the trigger for X is because you already know ahead of time that you don't have a trigger for Y.
Yeah, and then later, when you bind X to Y, you actually still don't need to run the trigger because the two
No, no,
variables are
no.
bound to each other.
When you run
So
this, everything goes to shit. You don't need to activate anything. But I want to keep. I want to go back to what you said. So the runtime is smart enough to figure out that, okay, do I have a trigger for this in a separate thread in the runtime, and do I have another someone else having a trigger for this? If I don't, I'm not going to activate neither. If I have only one, I'm not going to activate either. I will only activate if I have all of them.
yeah, because
That is
otherwise,
definitely not written in here. But okay.
because otherwise you have a problem where okay, the triggers are going to run even in like they may run in some situations but not others, which is something you should avoid um, because that might mess up.
I would always run them.
Actually,
If I was implementing the runtime, if I see the X, I would first ask myself, is this bound? No. Do I have an activation trigger for it? Yes, run it. I would do very naively like that. What you're saying is very more clever than what I'm saying, which
no,
is to
it's
pay attention
just
to all the variables involved.
well, actually, the book gets into it a little bit later. You need to. We've actually mentioned this already, but it didn't go into detail. It will go into detail later. Basically, the way you're suggesting is saying, okay, I'm going to run the trigger sequentially.
Sequentially.
Yeah, because you just said, okay, does X have a trigger? Yes, run it. You didn't even look at Y.
Because I need it. It's in the expression that I'm holding to suspend. It's
Actually, you
precisely
may not
because I
need.
need it.
Actually, you don't know if you need it. That's kind of the point.
No, like, how can I say? You need something. Like, in this case, this bind is gonna save our asses, right? But this also could be important. And how you gonna be able to tell which one is better? If you're not a person like us, a programmer.
You have to look at both variables, not just one.
That's okay. But like, if I was the runtime, my first instinct would be, okay, do I have a trigger for this? Yes, run it. Do I have a trigger for this? No, so wait. That's it. And I believe this would go to it would have the same result that this guy is proposing, right? Because I would say that x is 3, and then the y will be hanging until this runs.
Well, in this case, it would actually, but not in general.
How do you know that?
There's an example later.
An example later that's
I think it's way later though.
Yeah, but I'm not running them sequentially, by the way, because they are all in separate threads.
No, 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 no. You are forcing them sequentially when you do the equality.
Which equality? This one?
Inside of the if.
Oh, this one.
Yeah.
But it could be the other way around, no? So like, I ask her the question, do I have a trigger for Y? No. So just wait. Do I have a trigger for X? Yes. So run it. Doesn't matter in this case. You could swap the orders, the result will still be the same.
Hmm.
But okay, like tangent apart, if X is made determined, then the comparison will not execute since Y is unbound. Yeah, the comparison will not execute anyway until this thread runs. If it is only later on, if A is made determined, that the trigger on X should be activated. So like there is a priority order here. So like it is exactly what you said. If we can't figure out the triggers for all of them, we're not gonna run any of them. We're only gonna run them if there's only one piece missing, or we have the triggers for all of them. Being needed is a monotonic property of a variable. Once a variable is needed, it stays needed forever. Figure 425 shows the stages in a variable's lifetime. We are so fucked. It's already 40 minutes. Know that a determined variable is always needed just by the fact of being determined, as we said. Monotonicity is of the need property is essential to prove that the demand-driven concordant model is declarative. This makes sense. Like it doesn't prove that, but this in terms of intuition makes sense. Because and the reason is because if this was not guaranteed, then you're gonna have probably visible non-determinism. You need that after it's needed once to be needed forever. You need that.
Yeah. Turns out monotonicity makes your life a lot easier in the face of concurrency,
And
distribution,
in
what
math
have
as
you.
well. A lot of theorems use that assumption that F is monotonic.
Yeah, it just makes everybody's lives easier.
Uh, okay. Okay. So essentially, this paragraph is explaining to us that you first need to check for boundness of things before activating the triggers. That's essentially the priority. Okay. Okay. So this is the stages of a variable's lifetime. So you start being unbound, which is the data flow thing. Then you are unbound but needed, and then we go to the search of trying to determine whatever you are. It doesn't go
Uh,
into the whole spectrum of search, which there's a footnote somewhere saying that this is relational programming.
yeah,
So right now
that's
we only
later.
use the first path, probably the single path to search for how to determine this variable.
It's not even search. It's just okay. Um, I need the value of this variable to continue because I'm a primitive operation or whatever. Is there a trigger? Yes, there is a trigger. Is this the only thing I need to continue? Yes, it is. Run the trigger. That's kind of what it does.
Yeah, very simple algorithm. Then we see one example, and this is man, this is so terrible. I hate this with all my strength. But this is essentially how you interact with the lists, right? So this is two is tail and one is head.
Yeah.
Terrible. So this will look at the third element, and the reason is because you grab the tail of the first, which is another head and tail. You do that again, and then you pick the third element. So you do that, and then this will distribute to this, which has the bind construct that we just talked about. And then it does something weird as fuck, which is to talk about dynamic linking in this context.
Well, it uses the by needs to do it, so
So essentially, as far as I can tell, dynamic linking is when you're already running a program. So what is the difference between static linking and dynamic linking? Is that the dynamic linking happens at runtime.
yeah, you're loading the library codes that you need after the program is already running.
This allows for a very cool trick, which is hot reloading. But it also adds a lot of more complexity to it. But I find it interesting to read some portions of this thing. So dynamic linking is used to implement a general approach to structuring applications called component-based programming. Briefly, an application source code consists of a set of component specification called functors. A running application consists of an instantiated component called modules. I find it very funny that it calls the specifications functors, because functors in the context of ML is not exactly component specifications, right? It's a
Well,
module that
it
takes a
is
module.
well, which is a specification of a component, but it depends on something on another component.
Yeah, but it could have said that it's a module that takes a module. Because then
It's a
the
parameterized.
instantiated component being a module makes more, well, now it makes way more sense.
No. You see, a functor um, is a function that takes a module and returns a module, but it's not itself a module, right?
Well, informally, I've seen ML people talked about functors like that. Because it has a signature and it has an implementation, the functor. So it's kind of like a module that takes as an argument another module.
Yeah, but it's not really a module in the same sense that a function is not like a function on integers is not an integer, right?
To me, it's still a module because differently than the function, the functor has an MLI, like it has a signature, and it has an implementation, like a module does. But the only difference is that it
But you
takes another module as an argument.
but you can't use it until you call it with the argument, the concrete
That's
argument that
fair.
you want to
That's
instantiate
fair.
it with.
Yeah, but that's the thing. You need to instantiate it. Okay, that's fair. If you can't instantiate it, it is not a module. It's something else. That's fine. I guess that's fair. A module is represented by a record that groups together the module's operations. Each record field references one operation. Components are linked when they are needed. Their functors are loaded into memory and instantiated. As long as the module is not needed, then the component is not linked. When a program attempts to access a module field, then the component is needed, and by need execution is used to link the component. The only problem that I have with this is that this sounds very inefficient. Like, I think it would be way faster when you find that there is a first by need, you link all of it.
It's not that you do link all of it, but only when you try to access a field
Yeah, no, but you link
of
all
the
the
module.
fields when once one of them is needed.
Yeah, for that particular module, yes.
Yeah, but that's not what I understand from this. To me, this seems to be very fine granular by need, which means that okay, you need this one, I'm gonna link this one, and then I'm back. Oh, you need another one, I'm
Uh,
gonna link another one.
yeah, no, that's not quite it. What happens is, okay, you import the module that gives you a variable with which represents the module, right? But it's not actually loaded yet. It just creates a trigger. But then because of the trigger mechanism that only runs when you actually need the value, if you just pass the variable that holds the module's trigger around, that doesn't do anything. You have to actually try to access it somehow.
Hmm.
Which in the case of a module means trying to read a field, right?
Hmm. Okay, I guess that's fair. Okay, now we're going to combine the laziness with concurrency. Concurrency can make batch computations incremental. Laziness can reduce the amount of computation needed to get a result. A language can have neither, either, or both of these concepts. A language with laziness but no concurrency does co-routing between a producer and a consumer, which apparently is what Haskell does, and I didn't know.
Haskell is a bit more involved than that, at least the GHC version of Haskell, because that's also concurrent, right?
It says that Haskell and Miranda does coroutine.
Well, if you look at the standard Haskell, then yes.
Okay. Let us now give an overview of all the declarative computation models we know. Yeah, this is the table, right? So we're going to separate three moments. The creation of the variable is an entity in the language such that it can be placed inside data structures or passed to or from a function or procedure. The variable is not yet bound to its value, so it's a partial value. We call such a variable a data flow variable. The specification of the function or procedure call that will evaluate the value of that variable, which is related to the triggers portion of the store and it's what we were debating earlier, which is that this is not a bind, although I think it should, but I'm going to follow the book. And then we have the third moment, which is the evaluation of the function. When the result is available, it is bound to the variable. The evaluation might be done according to a trigger, which may be implicit, such as the need for the value. Lazy execution uses implicit need. Oh, and by the way, the reason we are calling lazy execution and not lazy evaluation, it's because it's using lazy evaluation to the streams implementation that we already have seen before. So there is
Uh,
some portion of the book that explains that, okay, we are calling it execution instead of evaluation, blah 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 blah. I don't remember where. We already probably passed through it.
yeah, I think it was in the previous chapter. But yeah, it's because in general you don't actually evaluate expressions. You have procedures that you execute which bind the variables, right?
Um, is that the reason? I don't remember. Are you
Like the
sure?
language model is slightly different from the lambda calculus. It's not actually expression oriented. So yeah,
I don't remember that being the
I,
reason, but that could be a reason. Uh,
yeah, no, it's way back. It's way back.
aha. To avoid confusion with lazy evaluation, which is sequential, we use the term lazy execution to cover the general case which can be concurrent.
Oh, it's not because of that then. It's
Oh, it's
because of
because of the
concurrency.
lazy evaluation, it's saying it's coroutining between the lazy function and the function that needs the result.
Okay,
So
it's
that's
because
why.
of that
We
then.
were
I
both wrong.
misremembered. Yeah, I misremembered. That's fair.
Okay, but the table is awesome. This table is very cool.
It's a
Actually, the
very
table
nice
by
table.
itself would be not cool, but because it has as a bonus these examples, now it's cool. So what are we seeing here? We are seeing two orthogonal axes. We have the these axes and these axes. So this one is eager execution versus lazy execution, and this one is sequentially by raw, sequential with data variables, and concurrent with values and data flow variables. So sequential with values and eager execution, we have scheme, ML, probably closure, um, LFE.
Not closure because closure is also concurrent.
Don't you have to do anything special by that? It's by default.
Well, you have threads, so you know.
Yeah, no, but it's not. Okay. Um, you probably also have threads in ML, but it's not as easy as with data flow variables.
But closure has data flow variables as well, actually.
Um,
They're called promises, and they are not as nice, but they are there.
okay, I didn't know that. I take that back then. And you have strict function programming, sequential values with eager execution. And then you have lazy function programming, which is Haskell here with 1, 2, and 3. And what does these numbers mean? The numbers mean the moments, and the ampersand means if they are being done together.
Yeah.
So 1, 2, 3, declaring and specifying coincide, evaluations done later, which is Haskell. Well, 1, 2, and 3, they need to all be done together. And then we have 1 and 2 and 3 together, which is declaring is done first, specifying and evaluating are done later and coincide. So this will be prologue, where you declare something first, and the specification and the evaluation, they are done together, yes. And then we have 1, 2, 3 separate. And I find it hilarious that the three, like this right corner, they don't have examples of languages, which is kind of funny. So
Yeah.
let's see. In a strict functional language with values such as scheme or SML, all the three moments must always coincide. So we have x equals this. So 1, 2 plus 2, 3. Then we have in lazy functional languages such as Haskell, we have 1 and 2 together and 3 separate. So I have a lazy function here, and I say that this is 1 and 2, and then I can just wait for it with in this case using a wait, but I can also use the by need protocol. Then I have in strict language with data flow variables, 1 may be separate, but 2 and 3 will always coincide. This is using Prolog and in Karuta for that matter. If concurrency is zero, this gives the data-driven concurrent model defined at the beginning of this chapter, which means that we also have the suspension mechanism from data flow. So I have an x here in a separate thread that I bind it in this if will hold for this comparison till x is defined. In the main driven concurrent model of this chapter, they can all be separate. So you declare it, uh, potentially in a separate thread. You're gonna have a lazy shit the binding it, and you have someone else needing it. Um, and this can be, yeah. So here are the threads, and all of this is kept declarative,
Which
which
is
is
crazy.
impressive. Yeah, which is crazy. Uh, so there is a summary here. Allowing the three moments to be separate gives maximum expressiveness within a declarative framework. For example, laziness allows to do declarative calculations with potentially infinite lists. Laziness allows to implement many data structures as efficiently as with explicit state, yet is still declarative. Data flow
Finger
variables,
trees come. Yeah, finger trees come to mind.
I don't know how to implement them, but I know that they are great. Data flow variables allow to write concurrent programs that are still declarative. Using both together allows write concurrent programs that consist of stream objects communicating through potentially infinite streams. I find this a little bit misleading because we already achieved this with explicit laziness. We are not gaining anything aside from convenience by using the implicit version.
Well, but it's still laziness though.
Yeah, but this conclusion could have been already described one section ago.
Well, it could have, yes, but it wouldn't have been as nice.
One way to understand the added expression is to realize that data flow variables and laziness can add a weak form of state to the model. Yeah, this is weird because we already have seen how data flow adds a state. That's why we need persistent data structures, for example, because we want to remove the little bit of statefulness that the data flow variables are adding to the model. But how is laziness adding a weak state form?
Memoization implies that you are mutating memory somewhere because you initially have something that's not bound to anything, but then you need it, so you force it, which is going to run a bit of code, and then you need to memorize the result so you don't run the code again.
Ah, okay, so it's because of the we're not running it again, and we need to save that somewhere. That's the weak form of state. Okay, why laziness with data flow must be concurrent? This is also very interesting. I haven't thought about it, but this is very true. I'm not gonna read this, but essentially the reason is if these two things were not done concurrently, these would deadlock depending on the order of execution.
Yeah,
Especially if they are done like sequentially this way, because this lazy function is being called here, so we are needing it because because this operation will suspend if you don't. And this
yeah.
is using z, but z will only come in the next one. But because you're doing it sequentially, this moment will never come. And there's a question: which of the models of Figure 426 has this problem? I think it's the middle one. This. Well, in this case, this, right? Because it needs to be lazy. This.
Yeah, that one.
Uh, yeah. Cool. Lazy streams. So it's essentially the same. Yeah, it's essentially the same shit that we did before with the producer and consumer, but using the implicit laziness this time, which in this case is just to add lazy to this function definition.
Very
Everything else is
nice.
essentially the same. Um, this is also true. The generate call does not need to be put in its own thread in contrast to the eager version. That's true. This is because generate creates a binding trigger and then completes. In this example, it is a consumer that decides how many elements should be generated. With the eager execution, it was a producer that decided. This is not true for the second version that we implemented. In the consumer, it is a case statement that needs a list pair, so it implicitly triggers the generation of a new list element X. To see the yeah, there he talks about resource consumption differences. So you pick the two versions and try to make 150,000, and this is what 15 million. With
Yeah,
150,000, there are no memory problems, and the eager version is faster. This is because the overhead of the lazy version implicit triggering mechanism. With 15 million, however, it's the table's turn, and the lazy version is only a very small memory space during execution, while the eager version needs a huge memory space. Lazy execution is implemented by the by need with the by need operation. And then we're gonna see, um, yeah, declaring lazy functions. In lazy function language such as Haskell, all functions are lazy by default. In contrast to this, the demand-driven concurrent model requires laziness to be declared explicitly with the lazy annotation. We find that this makes things simpler both for the programmer and the compiler. The first has to do with efficiency of compilation. Eager evaluation is several times more efficient than lazy evaluation because there is no triggering mechanism. To get good performance in a lazy function language, this implies that the compiler has to determine which functions can be safely be implemented with eager evaluation. So, um,
Strict, yeah, strict analysis. The GHC is notoriously good at this because it has to be, right?
um, yeah, but this is essentially figuring out um, which. Well,
Like,
I may be saying bullshit, but as far as I understand, this is trying to figure out which portions of functions can be eager.
yeah, basically trying to see, okay, this is always forced, so let's not use laziness here. The
Yeah,
compiler has to do this because the language itself doesn't give you an out, right? It's always everything is lazy all the time,
exactly. And the second reason is because eager languages are easier to implement.
and also
Multiple.
easier to yeah, and also easier to extend with non-declarative concepts because of order of evaluation concerns.
Uh, yes. For multiple readers, yeah, this has the bonus that if you have multiple readers, it's not going to be recalculating things because the faster
Very
one will
nice.
already have been triggered that. And then you have the bounded buffer, which, um, well, we're just adding laziness to stuff. So you
Look at
have.
how much look at how much simpler this is compared to the explicit buffer with explicit laziness that we had before.
I also think this is not as simple as it could be, at least for my monkey brain. Where as far as I can tell, this is requiring n elements from the producer, and then you are doing the loop there. The case is doing the triggering again the laziness to move forward in here, and then you're
If you look
putting,
at
yeah, and this
well,
is
yes,
triggering again.
yeah. Actually, if you look at the text, this naive version doesn't quite work. You have to use the one below.
No, this does work. It's just worse.
Yeah, because it forces. Oh, the text says this, right? It
Yeah,
forces the producer and the consumer to walk in lockstep. You don't really want that.
yeah, they need to walk together, and that's all we want. So then but this works. It's just worse. And this
Yeah,
one is better because it's essentially putting things in threads.
yeah, but look at how much simpler this is compared to the explicit buffering that we saw in the previous chapter.
Yeah, that was worse. But I still have to, maybe because I'm not used to it, but I still have to think a lot about it. Like, this is triggering the laziness there. This is also triggering the laziness, and this is triggering the laziness. Well, this is just explaining what Marinho just explained, and then we have an example of execution. So we do these lazy ints. Um, So the out1 requests one element. Calculating this element takes 1 second. Therefore, the browser first displays this, and 1 second later adds the first element, which updates the display of one future. Yeah, this is essentially what Marinho explained for the window thing. The window is interactive, which means that it will change after the state has changed as well. The notation future denotes a read-only variable. In the case of lazy execution, this variable has an internal trigger attached to it. And then you can do this type of shiz to see more elements. And after 4 more seconds, you're gonna have this thing. And then we go to reading a file lazily, which is very interesting. So the result of this function is gonna be this L here, right?
Yeah,
So what are we doing here essentially is we are reading block by block of the file, and I don't remember what the arguments mean.
it explains down here
Oh, if the
basically.
I is the size, so I being 0 means that we are done,
Yeah,
and the T is essentially something exclusive to the state of this function. So we just put it to nil, and we do the file close. Else,
Yeah,
we prepare the next call, which is a lazy function.
yeah, yeah. L and T together they form a difference list,
Yeah,
and T is the unbound tail at the end.
exactly. So that's how we do that lazily, read block by block. Reading blocks is much more efficient than reading single characters since only one lazy call is needed for a whole block. This means that read list lazy is practically speaking just as efficient as a solution in which we read blocks explicitly. When the end of file is reached, then the tail of the list is bound to nil and the file is closed. The read list lazy function is acceptable if the program reads all of the file, but if it only reads part of the file, then it's not good enough. And the reason why is because the file stays open during the whole execution of the program. This consumes valuable system resources, including a file descriptor and a buffer. And then you go to the Hamming problem, which is this picture. So we are essentially creating lazy streams of multiples of all of these things, and then the merge function makes sure that they are being concatenated in ascending order.
Yeah, this is basically the merge fragments from a merge sort,
Exactly.
except since we're producing the list from scratch, we don't need a full merge
Yeah, but
sort
this is
because
very
we're already.
declarative. Like, look at
It
this.
is. No, it's completely declarative.
Um, that's very nice. And then we have the touch the touch, like what a name. The touch function, which is essentially a take. Uh,
Uh, Kinda, not quite.
no, come
It's
on.
like a.
From an interface point of view, this is exactly like a take.
Well, we could also say it's exactly like a drop. The point is, you want to force a prefix of a potentially infinite list, so you say, okay, just touch the values that you want to pre-compute, right?
Yeah. There we go. Then we're going to see how to make these operations here lazy. And there's a difference between how we can implement them lazily. Because, for example, this append here, we are essentially linearly going through the A's, and at the end just putting on the tail the entirety of the B's. So it's incremental until a certain point. But there is a way to make it the full incremental by lazifying the B's. And then you get
Ah,
this.
yeah, I'm not sure if making it full incremental is worth it because you're basically adding overhead.
That's very true. Then we have the lazy mapping, which is just fine. Then we also have the lazy integer lists, which is an L from loop. Yeah, and then you can use also this for infinite streams. And then you have the lazy flatten. The lazy flatten is the crazy one, right? No, it's the reverse one that is the crazy one. This one is probably very similar to the previous flatten that we've seen, which to be fair, I already forgotten.
Oh, it just takes a list of lists and turns it into a list with one less level of depth, right?
Yeah, yeah.
Very normal stuff.
Very, yeah, this is where it's concatenating it back, like consing back, I guess. Cool. And then you have the reverse, right? The reverse is called a monolithic function. And the reason that which is very interesting, is that in order to get the first element of a reverse list, you have to go through all of it. So that's why we call it monolithic.
Yeah, you can use laziness to just delay the actual call, but once you require it, you have to compute the entire thing,
Yeah,
right?
it's doing it by hand on this paragraph. Uh, and then we have the lazy filter, which we're going to use later. And just a notice, the filter has the function as the last argument.
Map also
Terrible,
has the function. Yeah, map also has the function as the last argument.
terrible. Yeah, it does, and it's also terrible. Uh,
Uh, I think
persi-
it's.
Go on.
I think it would make sense in closure to try to do it like this. maybe because of thread first.
Okay, this is not
Um,
closure.
but this is not closure. You are correct.
Um, okay, persistent queues and algorithm design. So the first thing that we're gonna do, we're gonna exploit. Yeah, this is very deep. There's a lot of depth to this discussion because we're trying to compensate something with something else. Like I don't even understand if I fully understood this chapter, but we're trying to compensate the linear thing that we have to do from time to time on the check of the queues, which was the reverse. We were trying to compensate this with something else.
Yeah, we're trying to compensate it with the um, adding things either to the adding things to the queue or removing things from the queue, right? Basically, you want to delay the reverse until you have traversed enough elements that the amortized cost is actually constant. Because the reverse is obviously linear, right?
Yeah. Yeah, but I don't know if I fully understand how we are doing that in here. I just understood what you said, like in high level terms, that we are trying to compensate for the linear cost of something by doing something else.
Yeah, I mean, technically we were already doing this in the previous case with the ephemeral queue, except because the queue was ephemeral, you couldn't actually share the queue, like use it in two places and have it still maintain the performance guarantees, right? Here we're trying to use
Mm,
laziness to fix that, essentially.
yeah. Can we arrange the elements that F pay for the reverse? We can if you create the suspension when they are approximately the same. Then remove each element of F pays for the rest of the reverse. Yeah. So then there's a lot of actually that's the part that sucks. There's not a lot of code. It's just very deep. You just have to read this carefully and see that the reverse here is well this append is the lazy append and so on and so forth. And then there is the cheat here, which is we are trying to combine the append and the reverse, which is
Yeah,
actually
this is
very
to make
clever.
it yeah, this is to make it fully incremental, so you can have a worst case bound. Because otherwise, if you just use the normal reverse, that's monolithic. So you still have an amortized bound in that case. Here it's trying to again fix that. If you ever read like Okazaki, either the book or his dissertation, a lot of this comes from there.
Yeah, so we are combining the append with the reverse, which is very cool. Very cool. Traverses both F and R. Like this is doing a double traverse instead of doing one sequentially after the other.
Double duty.
During each iteration, calculates one element of the append and accumulates one element of the reverse. Very cool. Very cool. Okay, so laziness is able to shuffle calculations around, spreading them out, or bunching them together without changing the final result. This is a powerful tool for designing declarative algorithms. It has to be used carefully, however. Used naively, laziness can destroy perfectly good worst cases bounds, turning them into a more amortized bounds. Used wisely, laziness can improve amortized algorithms. It can sometimes make the algorithm persistent, and it can sometimes transform the amortized bound into a worst case. And essentially, uh, well, I think we should read this. We can use laziness to move from ephemeral to persistent while keeping this time around. Often we can get a modified algorithm A prime that keeps the amortized bound when used persistently. This is possible when the expensive operation can be spread out to be mostly incremental but with a few remaining monolithic operations. In a few cases we can go further and get a modified algorithm A prime prime with a worst case bound when used persistently. This is possible when the expensive operations can be spread out to be completely incremental. And then we have list comprehensions, which is essentially Haskell's list comprehensions. Uh,
Yeah,
so we are generating things and we're also adding a predicate to things.
Yeah, this is basically teaching you how to desugar list comprehensions into list functions, and then there's an exercise later at the end of this chapter that basically says, okay, now implement it as a syntax abstraction, which is kind of funny.
Yeah, and then we can implement it using the filter. So there it is. There you go. Yeah, you were essentially compiling this
By
notation
hand.
to this
Yeah, by
notation.
hand. Yeah,
Yeah,
just
not by
compiling by
hand because
hand.
GHC does that probably, but
Well, JC does that, but not Mozart, unless there's actually an implementation of that that the book doesn't tell us about.
and there's also a way to like not have to generate values that are extra than what you need. So it does a very
Yeah,
clever inequality manipulation thing here, which allows you to rewrite z as this, and this is actually generates less elements, half as many elements in fact, which is very cool.
it is.
And then 4.6, we're still over, but not as much as I thought. Well, I try to be more like brief on this final portion. The only thing I think I should understand better is this Q thing, because I'm still kind of not comfortable with the whole compensation process that we're doing. But I always suck on these complexity things, so I'm not surprised. Um, Probably I need to read like 10 more times and I will get it. I have questions about 4.6, so let's go there. So this is soft real time. The difference between soft real time is because soft is a lie. So we are not real time. We are kind of like ish, real time ish. And hard real time is really hard. So we need a special hardware for that. And here are the built-ins that we have for soft real time, which is delay, alarm, time.time. And then my first question is, why is Pong implemented differently?
Why is Pong implemented differently?
Yeah, what are we doing?
That's a good. That's a good question.
What are we
Let's
doing?
see. Hmm. Oh, it's because ping counts backwards.
But this doesn't make a difference and serves no purpose aside from counting.
That's fair.
Yeah, so this is just for lols. Okay. Uh, yeah. Okay, so this is essentially a ping pong process that is the pong it has a greater interval. And there's a question here. Can the same thing happen with two pongs? Can we see two pongs in a row? The answer is yes, but that's because of the overhead of the runtime and also depends on the scheduling algorithm that is being used. Like
Yeah, it's because this
there's
is
many
yeah,
reasons.
because this yeah, this boils down to yes, because this is just soft real time. It's not hard real time, you know.
No, yeah, but I think it's expecting a more detailed answer, and the answer is because of this thing. It's because delay only assures minimum suspension time.
Yeah.
A single standalone application. So this is how you do the make a functor. So you call this. So there is a functor. This is the module that you're gonna use as an receive as an well. You're gonna receive this as an argument because you're gonna use it in here. This is how. Yeah, this is all not important. This is what I want to ask.
Okay.
We would like to invoke an action exactly once per second, given the local time as argument. We have three operations at our disposal: delay, time, and OS local time. Time returns the number of seconds since January 1st of the current year, which sounds terrible. This sounds very terrible. And we also have
Yeah. I wouldn't like that as a primitive either.
OS local time, which returns a record giving local time accurate to 1 second. And we have delay as we seen before. And then we have this new ticker, which uh,
Yeah, it's kind of split up because
yeah.
there's a
So we have the
figure in the
loop
way.
function, which is asking for the local time at this moment. Then we wait 1 second, and we tail call. And yeah, the body is essentially calling the like start kicking off the loop. This function creates a stream that grows by 1 element per second. To execute an action once every second, create a thread that reads the stream and performs the action. Boom. And this is the problem because this is almost extended almost exactly 1 per second. And the reason it's almost is because of the reasons we talked about before. The delay only assures the minimum.
Yeah.
Every once in a while, 1 second is lost. Successive elements of the stream show a difference of 2 seconds. However, there is one good point. The same second cannot be sent twice, since delay 1000 guarantees a delay of at least 1000 milliseconds to which is added to the execution of the instructions in loop. This gives a total delay of at least 1 second plus an epsilon, where epsilon is a fraction of a microsecond. Well, actually, we don't know. This can be a microsecond, a millisecond, whatever the fuck. How can we
Yeah.
correct this problem? And this is my problem. I have no idea how this is correcting anything. A simple way is to compare the current result of OS local time with the previous result, and to add an element to the stream only when the local time changes. But this is always true. No? This is like every time you call local time twice, it will always be different. Different. Aside from
Not.
having multiple cores and each thread is
No,
running in each
it's
individual core.
it doesn't because of granularity lemons. Local time gives you the time in seconds, no?
Accuracy up to 1 second.
Oh yes, but it gives you the time in seconds since the beginning of the year, right? Which means if you call
No,
it
no, no, no,
twice
no,
in
no,
the
no, no,
same.
no. That's time. That's not local time.
Oh.
Local time does this thing. There. A record giving local time accurate to 1 second.
Well,
This is
accurate
like
to 1 second.
local time. So this has hour, minute, second, and that's it actually. It's
Oh yeah,
all.
but yeah, but it's only accurate to 1 second, which means if you call it twice in the same second, you get the same result.
Fine. But then, like, that's my first question. And that's actually true. I forgot that it's up to 1 second. But then it comes the other thing, which is look at what we're doing. We call loop with this local time. Let's assume, for the sake of the argument, that this is equal to up to the second. And then we do a delay of 900 milliseconds, right? And
Uh,
like, what are we doing? Are we trying to compensate? Like, what are we doing here?
yeah,
What are we trying to compensate for?
we're trying to compensate for the fact that delay may actually wait longer than the number you give to it.
But why 900? Why not 850?
I
Who
mean, you
is
could
getting?
do
Where
that.
are those numbers coming from?
Well, you could use a lower number, and the text actually mentions that later in the following paragraph. Or following page, I should say. I don't remember the exact
No,
paragraph.
but it's saying this version guarantees that exactly 1 tick will be sent per second. If
If
this does,
delay always delays for at most for less than 1 second, basically.
no, but we don't know that, right?
Yeah, we don't. That's why it's saying this condition holds if blah blah blah.
No, no, but let's say, just for the sake of the argument, that delay always delays for less than 1 second. Delay is 900. Always delays for less than 1 second. Let's say that it delays for 990 seconds. How do you know that this will happen exactly? How do you guarantee that this exactly 1 tick will be sent per second?
Because you're
Ah,
going to.
I know why. It's because if this is 990, they will be equal up to the second.
Yeah.
That's why. Okay, so it's the two things combine. You put a gordurinha, like a little bit of
Padding.
distance, a padding,
Bet-
yes, between the 1 second and the delay value, and you cross your fingers that this will be enough to make T1 and T the same.
yeah, basically the way this works is every now and then you're going to call the function twice in the same second, but it's only going to emit the value once because of
Yeah.
the
Okay,
time
now I
check,
get it.
right?
It's both two things combined. Okay. The later condition holds if there are too many there are not too many active threads and garbage collection does not take too long. One way to guarantee the first condition is to give the loop thread high priority and all the other threads medium or low priority. To guarantee the second condition, the program must ensure that there is not too much active data, since garbage collection time is proportional to the amount of active data. This version has the minor problem that it hesitates every 9 seconds. That is, it can happen that OS local time gives the same result twice in a row, since the two calls are separated by just slightly more than 900 milliseconds. This means that the stream will not be updated for 1.8 seconds. Another way to see the problem is that 10 intervals of 900 milliseconds are needed to cover 9 seconds, which means that nothing happens during one of these intervals. So this is essentially saying that this will be a multiple of 1 second at some point, and then you're going to have a problem.
Yeah, basically you don't have a steady clock. It kind of every now and then you have a second that's kind of longer than the others.
Yeah. How can you avoid this hesitation? Simple way is to make the delay smaller with a delay of 100 milliseconds. Well, it will come eventually, but it's gonna be way in the like more in the future.
Yeah, you're basically wasting work, right? Because if you, let's say, with the delay of 100 milliseconds, and let's assume that you don't take more than 200, um, you're going to like call the function like 5+ times per second, and only one of them is actually going to do something, right? That's kind of wasteful.
No, but it will be wasteful at some point. You cannot avoid this, right?
Yeah,
A better way to avoid hesitation is to use synchronized clocks. That is, we create a free running counter that runs at approximately 1 second per tick, and we adjust its speed so that it remains synchronized with the operating system time. So this is essentially, this is kind of funny because this is serving as a clock mechanism, but because you don't have access to the real clock, which is using like a crystal, and it's very precise and it's very reliable, we are trying to mimic one in software, but because they like it's not perfect mimicking, you have to try to compensate yourself.
yeah,
Like you're trying like a little bit faster, and oh, too fast, go slower. Too slow, go faster, and you keep doing that all day.
yeah.
Uh, the loop has a counter, and this is actually this kind of sucks. OS should have OS access to it.
I mean, it probably does, but well, this
Actually,
book is.
I'm not even sure how easy it is to do that. Like with a microcontroller, you can easily do that, but with a full-blown PC, I don't know if that's actually exposed. I'm not knowledgeable enough on that one.
I think it would depend on the operating system and also on the specific hardware that you're actually using because I'm not sure where the clock actually lives. Is it in the motherboard
Yeah,
or is it inside of
motherboard.
the? Okay. Well, if it's in
As
the
far as I
side of the
remember, I may be wrong, but
motherboard,
I think it's in the
yeah,
motherboard.
if if it's in the motherboard, then it's definitely like it's hardware dependent, right?
No, but all hardware has it. Like the CPU must have a trace for it. So we compare the counter value to the result. If the counter is lower, we speed it up. Otherwise, we slow it down. So this is just funny. And then we are done. Limitations and extensions of declarative programming. Okay, this was very fucking long. Uh, but let's talk about what we're gonna be doing next. So I think we should try to finish 4. Is that doable?
Can we finish four?
That sounds like a lot, but I think it's gonna be the best because I was like, if you take a look,
Yeah, yeah, I was thinking about it because I actually read until the end of chapter 4 earlier today because I kind of got carried away a little bit with reading. I like this book a lot.
yeah. So this is what
Um,
29 pages. Uh,
yeah, and
I
we
think we should
probably
do it because this is gonna be too little, and if we do both these two, this is gonna be too little later. So I
yeah, I
think we'd rather do
agree.
all of it.
We probably won't spend too much time on 4.8 because like we know Haskell, right? You know a lot because you work with it. I know some because I studied it. So yeah, I don't think yeah, I think it's doable. Try to finish. Oh, there's historical notes as well. You have to take that into account. Although that's just like
1 page.
1 page.
Yeah, and although I know I worked with Haskell, I confess I'm not very knowledgeable about GHC internals. So I
But this
probably
doesn't
gonna
go.
learn things.
I don't know, but this doesn't actually go into GHC internal, so it's probably fine.
Uh, cool. So I'm gonna finish the recording now.